Homework from Friday.
Oh, from Friday.
Yeah, the other one.
Oh, okay. I haven't even. Great. Okay. Thanks, Nelson. Yeah, I haven't even looked at that homework yet. All right. I see one person is there. That's good. So you know we're gearing up to test number 3, and which is a week from Wednesday. So you've gotten some things today. You've got the take-home quiz, which is due that day, and another homework set, which is also due that day. And in addition, I have a practice set, which is, of course, something I don't collect. It's strictly for your practice. And the solutions to those will be posted on Sunday afternoon, like I've done with previous tests. All right? I should have the homework that you turned in on Friday. I should have that back to you on Wednesday. All right? I have not even looked at it yet, because I spent my time with all this kind of stuff. The facts and formulas to know for test 3, I'm still working on that. What is this? Samuel, yeah, the test is, Samuel, you might as well tell all of your classmates that the test will pretty much be on Wednesday from here on out, okay? All right. Well, you're very welcome. I certainly do want to let you know. Okay. Anyway, facts and formulas, that'll be forthcoming. Okay. So anyway, what we're going to do today is try to make some headway in this section 11.9. And as I heard someone say, there are a lot of sections for this particular test, and I know. What can I say? At least we're not doing section 11.11. So that's something to think positively about, all right? So anyway, section 11.9 has to do with representing functions as a power series. All right. And there's a central tool for this that we'll be using throughout this entire section. Central tool or fact. And that's this. If the absolute value, I'm going to use a new variable, call it u. If the absolute value of u is less than 1, then 1 divided by 1 minus u is equal to the sum of 1 plus u squared plus u to the third plus dot, 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 which equals, of course, the infinite sum as n goes from 0 to infinity of u to the n power. And this diverges if the absolute value of u is bigger than or equal to 1. And this really is not a new fact at all. This is a geometric series. All right. The common ratio is u, because we keep multiplying things by u. The common ratio is u. All right. And the first term in this series is the term 1, when n is equal to 0. And we know that the sum of a convergent geometric series is a divided by 1 minus r. So in this case, that is equal to 1 divided by 1 minus u. All right? Okay. I want to point out that this is a minus sign here. It is not a plus sign, a minus sign. And as long as that absolute value of u is less than 1, I can represent 1 over 1 minus u as this infinite series. Okay. Question, first of all, about this central fact. So this is the core of this entire section of what we're going to be doing. All right. So we're going to be going through a series of examples about how we can use this particular fact to express other functions as power series. Okay. So the first one is this. 1 plus x squared, express it as a power series. Express as a power series. And also find its interval of convergence. Find its interval of convergence. All right. What we have to do is we need to get it in the format of 1 over 1 minus u, in that general format. We need the general form 1 over 1 minus u. All right. Now, in this case, notice we have a plus sign in the denominator. Well, I can convert that plus sign into a minus if I have a double minus. So I can change 1 over 1 plus x squared into 1 over 1 minus x squared. Little trick. All right, just a double minus makes a plus. Now I have my minus sign that I need. Notice we have a 1 here. We also need to have a 1 there. Now this that I have in parentheses, this minus x squared, this is my u. All right? Now, this is going to equal then, the summation as n equals 0 to infinity. Well, what does my 1 up here? It says n equals 0 to infinity of u to the n power. So we're going to do that here. But instead of writing u in parentheses, I'm writing minus x squared, close parentheses, and I'm raising it to the nth power. Now this is going to be the case if remember, if the absolute value of u is less than 1. In this case, if the absolute value of negative x squared is less than 1. Now when is that going to happen? What range of values is going to make the absolute value of negative x squared less than 1? Well, it's certainly going to be fractions, yeah. What's the range of values that we can have here? Between 1 and negative 1. Certainly with the absolute value, I can get rid of the minus sign there because the absolute value turns everything positive anyway. So we're looking at the absolute value of x squared less than 1. All right, so basically that's going to be x squared is also always positive, right? So that's the same as x squared being less than 1. And the only values that work there are between -1 and +1, okay? That's going to be x less than 1. That's going to work. But also, if it's greater than negative, squeeze between -1 and +1, and we square it, we're going to get something that's less than 1. So the range of values for which this thing converges is anything between -1 and +1, but not the endpoint, only between those two values. Before I go on, does anybody have a question about how I determine that interval of convergence? All right, and now this thing, all right, this is fine in this format here. I could fiddle with this a little bit, and we'll do some of this fiddling later, especially. So this is my power series minus x squared raised to the nth power. But this is really -1 times x squared raised to the nth power, right? So I can break it apart as two powers. I can break it apart as -1 raised to the nth power times x squared raised to the nth power, like that, for starters. And then another thing I can do, if I so want to or need to, is I can recognize the 2 raised to the nth power. I multiply the exponents together, and I get 2 times n. So another way of writing this convergent power series is -1 raised to the nth power times x raised to the 2n power, right? So those are a bunch of equivalent answers here for this. So that's the first example. Any questions, doubts, concerns about that one? Okay. So let's look then at this one. 1 over x plus 2, and it's the same deal. We want to express it as a power series, and we want to find the interval of convergence. Now remember the form that we have to aim for. The form we have to aim for is something in the form of 1 over 1 minus u, some u. Okay, so this is a 1 here. What do we have here? We have 1 over x plus 2. Well, I can certainly write that as 1 over 2 plus x, all right? I'm just switching the terms in the denominator. Now, this is a 2. I want a 1 for this formula. You have to have a 1. So how can I make that 2 into a 1 while at the same time not fundamentally changing my expression? Write it as 2 over 2, but if I write it as 2 over 2, what else do I need to do if I'm going to do that? Because you can't just change it.
You can do 1 plus 1 plus x. Right.
That won't ultimately help us much. You would see it would. Well, I see what you're saying. Yeah, that's a thought, but that's not where I'm going. But let's hold that thought for a second. Yeah.
Multiply by 1 over 2, and then make it 1 plus x over 2.
Okay. So Kyle is saying, why don't we bring a 2 out? Let's do this. We have a 1 on top. Let's just bring out a 2. And then that 2 that'll become a 1 inside the parentheses. Now, I have to have an equivalent expression, so how am I going to represent the x term?
X over 2.
X over 2, right. like this. So therefore this, first of all, I'm rewriting, let's put it this way. I'm rewriting this as 1/2, 1 over 2, times 1 over 1 plus x over 2. We're halfway there. But we want a minus sign here, not a plus sign. So I keep my 1/2 and do the trick that we did with the other one. I write 1 over 1 plus x over 2 as 1 minus negative x over 2, like that. All right? And I'll get back to your thing because that could actually be something interesting. I think that I'll look at it. All right, so this is our general 1 over 1 minus u format, all right, that we want. But here the u is going to be minus x over 2, what we have in the parentheses. Okay, so if that absolute value of u is less than 1, i.e., the absolute value of minus x over 2 is less than 1, then this equals 1/2. Now don't drop the 1/2, all right? Got to keep the 1/2. And then we're going to represent the rest of it as the power series n equals 0 to infinity of minus the u, minus x over 2 in parentheses to the n power. Okay. All right. And again, then we can do the same kind of what I call fiddling with this as before. Keep the 1/2, n equals 0 to infinity. I can bring out a -1 just like I did before because I've got a minus x there, minus 1 to the n, and then my x will just be x to the n power. And I could even separate it out further then. And then the 2 is on the bottom. It's also being raised to the nth power. I could put 2 to the n power down in the denominator like that. All right? And now, let's see here. Let's look at the interval of convergence of this thing. This absolute value of minus x over 2 has to be less than 1. Well, that's, of course, the same as positive x over 2 absolute value less than 1. So that means that x over 2 has to be squeezed between -1 and +1. And if I multiply by 2, I have that x is squeezed between -2 and +2. Another way I could have done this is the following. If I've got the absolute value of x over 2 less than 1, I could just multiply both sides by 2 and have the absolute value of x less than 2, which is also the same thing, squeezed between -2 and +2, not including the endpoints, all right? Let me look at what Will has suggested. So there's a little bit of fiddling with this. We have to get it in that general format, 1 over 1 minus u. Then we can represent it as that sum of the u's to an n power. Okay? Let's see what the suggestion was there. 1 over, it was, okay, 2 plus x. Let's see what would happen. 1 over 1 plus 1 plus x, all right? We have to use the 1 over 1 minus u format. So let's see, how could I fiddle with this to do that? I can fiddle with that bottom.
Do the double negative.
Do the double negative, yeah, put 1 minus, and then what expression would I have inside the parentheses then? -1, and what else? And minus x, right. Exactly. So I could represent it like this, and then this would be my u. Okay, for the most part, I'm going to say do it the first way, all right? But this is another possibility, you know? And so therefore, this would be the summation n equals 0 to infinity. Now, I put whatever my u is in the parentheses, raise it to the nth power, and that's the general form of my power series. Now, again, both of these terms are negative, so I can bring out a -1, raise that to the nth power, and then what I'm left with is 1, +1 plus x raised to the nth power like that, and from n equals 0 to infinity. And it's going to have the same radius of convergence here. We need the absolute value of u to be less than 1, which means that we need -1 minus x, absolute value, to be less than 1. So that means +1 plus x has to have an absolute value less than 1. So let's see how that's going to work. 1 plus x has to be less than 1, has to be greater than -1. Are we going to have a different, oh, we're going to have, actually, we're going to have the same, what is this? Yeah. Is that right? Minus, yeah. Okay. So in this case, interesting. The reason we're going to have something different here is because we're offsetting it by 1. So basically, we subtract 1 from all three parts here, and I get -2 on the left, I get my x in the middle, and I get 0 there. So this is interesting. Okay, did we do everything? Make sure everything's okay here. Right. The numbers, they don't lie. All right. So therefore, we have here, x has to be between -2 and 0 then for that one. Okay. So we can have, this is an interesting example we're showing, we can actually have different power series representations where it's valid for different values of x. All right. Okay. It depends on how we choose to expand it. But the point that I want you guys to remember is that however you pick the u, and I really want you to go with the first case that I did with this, because that's how I'm going to be doing it, and that's what I'm going to be looking for primarily. And then you have to have that absolute value of u be less than 1, and so then you get your values of x that work for you. Okay. All right. Let's look at another example here. We just want to go through a bunch of stuff here so we can see how this works. Now here we have x to the third over x plus 2, and with the same questions represented as a power series and find the interval of convergence. Now, we've already done 1 over x plus 2. All right. And I'm going to go with the first way of representing that. We found that 1 over x plus 2 is equal to the summation as n equals 0 to infinity. I'm going to do the way we had written it out at the very end. -1 to the n times x to the n divided by 2 to the n. Okay. And this is for absolute value of x less than 2. All right, now we're wanting to do x cubed over x plus 2. All we have to do is this. X cubed over x plus 2, well, that's equal to x cubed times 1 over x plus 2, right? We're just multiplying it by x cubed. So I can just take that x cubed and multiply it by my representation of 1 over x plus 2. So I have x to the cube in front, and then I have my summation, 0 to infinity, -1 to the n, x to the n, all over 2 to the n. And when we are multiplying a power series like this, we can bring that into the body of the power series. It's basically distributing it with an infinite number of terms, yes? Why is it less than 2? We just found, in this case, when we did this, u was equal to minus x over 2, the first way that we did it, all right, and we look at the absolute value of that being less than 1, and that brought us to x having to be less than, absolute value having to be less than 2, all right? Okay, and so we can distribute that in, so we have a final answer here, n equals 0 to infinity, minus 1 to the n. Now, what's my new power of x going to be then inside if I'm distributing x to the third? No. X to the 3 plus n, right, or n plus 3. When you are multiplying two things with the same base, you add the exponent. All over 2 to the nth power. And so that would be our representation of x cubed over x plus 2. And again, for absolute value of x less than the number 2. Okay. All right. Again, another one here. This time we'll have x over x squared plus 4. All right. So first of all, I want to point out that x over x squared plus 4, I can rewrite that initially as x times 1 over x squared plus 4. Because remember, we're aiming for a 1 over 1 minus u type of representation. So now I've got at least a 1 up there in the numerator. Now we're going to do the same kind of thing. Of course, this is the same as x times 1 over 4 plus x squared, where I just put the 4 first in the denominator. And I need to make that 4 a 1, just like we previously had to make that 2 a 1. So if I draw out, multiply that by 1 over 4, the 4, I would then in my parentheses have a 1, and then for my x term, what would I have? X squared divided by 4. We cannot fundamentally change the expression. So if I'm multiplying on the outside by this 4, I have to be dividing on the inside by 4. So x squared over 4, like that. Okay. All right. So let's see, we're almost got it in that format. So this is x times 1/4 times 1 over. Now I need a minus in here, so I'm going to do that double minus again. 1 minus negative x squared over 4 in parentheses. All right? So this here is my 1 over 1 minus u. And so this is going to expand as, let's just combine this as x over 4 instead of x times 1/4. X over 4 times the summation, n equals 0 to infinity, and then I put whatever I have for my u, which in this case is minus x squared over 4, and that is being raised to the nth power. Okay. And now this is going to work if the absolute value of u is less than 1. So that's if the absolute value of minus x squared over 4 is less than 1. Now that's going to be the same as absolute value of x squared over 4 less than 1. And if I multiply both sides by 4, that's the same as x squared, I could have just written x squared being less than 4. And so what range of x values is that going to work for? X squared is going to be less than 4. Right. Anything between -2 and +2, that's going to work for. Does everybody see that those would be the values that would work for? Okay. So that would be this is my interval of convergence. By the way, with these, we do not have to check the endpoints because we know that with geometric series, if U is greater than or equal to 1, it diverges. So I don't have to check the endpoints with this. Yeah, Jenna?
If we would have distributed X over 4, would that change our answer?
It won't change the interval of divergence, of convergence. It will not change that. That's strictly based on the U. Let's do a little messing around with this to kind of change this, because we've got an X over 4 here. So I could bring that X over 4 inside, so we could have the summation as n equals 0 to infinity. Well, I tell you what, before I do that, let's fiddle with that, with what's behind the summation sign there. That minus x squared to the n power, I'm going to bring out the minus 1. That's going to be raised to the nth power. Now I have x squared being raised to the nth power. So Jenna, what would be my exponent there for the x now? 2n. And then it's all over 4 raised to the nth power. I've just split it apart. That's all I've done. All right, now let's distribute the x over 4 inside. So now we have the summation as n equals 0 to infinity. Okay, minus 1 to the n, that doesn't change. Now I have an extra x in here that I'm going to put over. So what's my new exponent going to be? 2n plus 1. We add the exponents, and then it's over 4 to the n. But remember, if we're also putting in a 4 down in the denominator, so what's my new exponent for 4 going to be? 4 to the n plus 1, because we're dragging in that 4 in the denominator. Okay. All right. So a little bit of manipulation has to be done here with some of these in order to get it in the right format so we can use the central facts of this section. All right. Now, what we're going to look at next then is looking at a power series. We can take its derivative and do its antiderivative, and it's really, really easy. Okay. So this part here is about finding derivatives, and I'll just say integrals of a power series. Because we're going to use this, maybe not get to it today, but we'll start looking at this on Wednesday for sure. Now, this is the fact. For the values of x that have the power series converge to a nice finite number, we can just take the derivative term by term, or we can take the integral term by term. So let me put this down here. For the values of x, such that the power series converges, and what are we talking about here? We're really talking about the interval of convergence. Interval of convergence. We can find the derivative. We can find the derivative and the integral term by term, which is really easy. Okay. So let's just show this in general here. Let's have a function f of x that is a convergent power series. So we have it as the sum of some coefficients times, let's even have it centered around a. X minus a to the nth power, n equals 0 to infinity. And let's say r is equal to the radius of convergence. i.e. x minus a absolute value has to be less than r for it to converge. So this is a power series that is centered, what we call centered at a, all right? So then the derivative of this is just the sum of the individual derivatives. So we have the sum from n equals 0 to infinity, and then we just take the derivative of the expression that's after the summation sign. So we bring down our exponent, multiply it by the Cn, and we reduce the exponent of the x minus a by 1. And then with the chain rule, we don't have to do anything further because we just have a 1 there. So this would be our derivative of the power series. And this is also same radius of convergence. So that's important to remember. Same radius of convergence. Right. And we can do the same thing for the integral, or indefinite integral. We can take the integral of f of x dx, and it's then going to be the sum of the integrals of each of those terms. So we're going to do the summation, n equals 0 to infinity, and I'll do it in 2 steps here. So that'll be the integral of, here it is, Cn x minus a to the nth power dx, okay, each of those terms. And so that's an easy antiderivative to get. So we have summation n equals 0 to infinity. We keep the Cn. X minus a, remember within integrals, we have to raise it to the next highest power and divide by the same. So this is going to be x minus a raised to the n plus 1 power over n plus 1. All right. And then at the very end here, we only need one general constant. We don't need an infinite number of general constants, plus c. All right. So with this case, for those of you who are concerned about it, if we want to think of it, I just let u equal to x minus a, and we end up with that answer, okay, for the antiderivative. Okay. And again, it's the same radius of convergence for that one also. So do we see we just do term by term, either the derivative or the integral. Now what we're going to do with this fact, one of the things we're going to do with this fact is we now will be able to express other kinds of functions as a power series using these facts that we just went over. It's kind of interesting, I think. So here, we can now get other types of functions represented as a power series. Okay. And I know that so far I haven't really made it real clear as to, well, what's the big deal about expressing a function as a power series? I mean, why are we even doing this, right? For starters, computer systems that find integrals and derivatives frequently use power series approximations. In other words, they go out so many terms. They don't go out to an infinite number of terms. They go out so many terms in order to find the value of something, okay? Because all they need for whatever their system is a certain degree of accuracy. You know, they don't need accuracy to the 500th decimal place, all right? And so by representing certain things as power series, we can get that. Another thing we can get with this is that we can find integrals that we could not find before. And before I go on to this, let me just show you this one. And I'm not going to do the problem, but I think earlier I had given you a list of some functions that we couldn't get the antiderivatives of in the ways that we had available to us. And this was one of them right here. The antiderivative, I believe, of e to the minus x squared. Now, we'll see, not today, but we're going to see how we can express this thing right in here as a power series. We'll be able to get the integral or antiderivative of a power series just like we had just shown, and I can then show this as a power series, which will be good enough for practical purposes as far as if we need that antiderivative. Okay. So, all right, let's get back then to what this other thing we're talking about. Let's look at this example. I think this will probably be it. Express 1 over 1 minus x in parentheses squared as a power series, PS, and get its interval of convergence. And get its interval of convergence. Now, notice what we have here. We have something squared in the denominator. Now, what we want to aim for with this technique is 1 over 1 minus u. Now, you can look at this. Let me put parentheses around this. This is 1 over 1 minus u to the first power. Now, if we take an antiderivative of something which has a square in the denominator, we're going to end up with something which is just has the power 1 in the denominator. So let me show you this here. Let's look at the antiderivative of 1 over 1 minus x squared. Let's see what we get here. Well, we're going to use a basic substitution. Let u equal 1 minus x. So du is equal to minus dx. So therefore, minus du is equal to dx. So what we come up with here is 1 over minus 1 over u squared du with our substitution. And so this is minus u to the negative 2 du, just rewriting the exponent. And now let's get the antiderivative. Well, that's going to be minus u. We add 1 to the exponent, so that's going to be a negative 1 over negative 1. And that, let's see, this is going to be, I've got a double negative here, so that's going to be plus 1 over u as my antiderivative. Now, what is our u that we used here? Well, that is 1 over 1 minus x. So now I got the antiderivative. Now I have something that I can use to get the power series representation. I have 1 over 1 minus x. That's almost handed to me on a plate there. So I can represent 1 over 1 minus x. This is my u is equal to the x. That's going to be the summation of x to the n power as n goes from 0 to infinity, as long as that absolute value of x is less than 1. All right. So let's see what we've got here then. So this is what we've got. We now have that the integral of 1 over 1 minus x squared dx is equal to this summation, this infinite series, n equals 0 to infinity of x to the n, as long as the absolute value of x is less than 1. We show this antiderivative is 1 over 1 minus x, and we can get the infinite series for that. So with this in mind here, if I have that the antiderivative of 1 over 1 minus x squared is equal to this infinite sum, Remember, I want to find what 1 over 1 minus x squared equals. What can I do to the other side? If I know that that the antiderivative is something, then the what of the antiderivative gets me back to the original function. What's the opposite of an antiderivative? Derivative, right. So if I know the antiderivative is equal to this thing, this function, this series, then the function itself, 1 over 1 minus x squared, has to equal the derivative of that series, right? So mull that over if that's not immediately sinking in. So this is equal to the derivative of this whole series, n equals 0 to infinity of x to the n dx. Okay? Back to Calc 1 with a fundamental theorem of calculus. So we're almost done with this thing. So now, as long as x, the absolute value of x is less than 1, I can do the derivative term by term, right? So this is equal to the sum of, from n equals 0 to infinity of, let me just do a couple steps with this. I'll just bring the derivative inside, the sum of the individual derivatives of x to the n, and so this is the sum n equals 0 to infinity. Okay, that's a week 2 derivative to get from Calc 1. Bring down the n times x, lower the exponent by 1. This, and then that's if absolute value of x less than 1. So this right here, with this little tricky little move here of seeing that an antiderivative will get me in the right form that I want, gives me, and then I take the derivative of that, gives me my answer as a power series. Okay? All right. I think on that note we will, too late to start. We'll be looking further at this kind of example with other kinds of things next time. Okay. Monday class just goes like we just started and it's over with. Right? I heard that. Yeah. It's a 5-hour course.
Well, you said it'd be shorter, and
I lied. Well, but no, I leave you lots of space to do the answers. So you can't just go by the number of pages.
No, I look at the number of problems.
How many problems?
12.
12? Huh?
Last one had 15, right? Okay.
All right. Yeah, it's shorter then. 12 is less than 15.
Okay.
Are you feeling better, Kyle?
Yeah, I'm getting out of the last time.
Good. You look a little less pale on the cheeks than that, so that's good.
Start drinking more. Maybe.
You think that might? Well, yeah. Oh, there you go. Get a good sunburn.
We get a burn. Have a good rest of your day.
All righty.